Okay, so questions. Questions? Any questions? Any problems?
Number 5 on the chapter 12 homework.
And the homework is due tonight, right?
Yeah.
We have to do 3 more homework assignments after chapter 12 before the break. And one of them is relatively interesting. We'll see. Oh, this problem, I think, didn't I solve this problem? No? Are you sure? I know that I solved it, I just don't remember where. But it is, let's see. Oh, don't have. Okay. So problem 5 from the homework assignment on chapter 12. Problem 5 from the homework assignment on chapter 12. Okay. So it is a pendulum problem and thermal expansion problem at the same time. And look, so you have this, the period of a pendulum. So this capital T in this problem is going to be period. And temperature is going to be lowercase t. So the period of a pendulum is given with 2 pi square root of the length of the pendulum divided by 9.8, the acceleration of gravity. And when you heat up this wire, the length of the pendulum increases, and therefore you are going to obtain a different period. So let's say that initially the length is L naught and the period is T naught. So when you increase the temperature, the length becomes L equal to L naught plus coefficient of thermal expansion alpha times L naught times temperature change delta T. The temperature change for my version of the problem is 152. The initial length is not given. So here is another example how you cannot work with numbers, and you shouldn't work with numbers when you can avoid that. So with this new length, the period of the pendulum is going to be, and I'll write it right here, or I'll write it here. The period of the pendulum, the new period of the pendulum is going to be 2 pi square root, and instead of L naught, I'll write the new length, L naught plus alpha L naught delta T. You have to read the coefficient of thermal expansion for this material, brass, from a table, divided by 9.8. So you're given that this is 2 seconds. And you may be tempted, of course, to calculate from here L naught, the length, before heating and warming up the wire. But it is easier to do the following thing. Divide this equation to this equation. So on the left-hand side, you're going to have T divided by T naught. Remember, T naught is 2 seconds. On the other side of the equation, you're going to have 2 pi square root of L naught plus alpha L naught delta T divided by G, and all of this divided by 2 pi square root of L naught divided by G, like this. And now you're going to get many cancellations here. So you can combine those 2 square roots as a single square root, do the division there. So if you want, write it like a single square root, and you have division of fractions, L naught plus alpha L naught delta T divided by G, and here you have L naught divided by G, right? And you cancel everything that you can cancel. You can cancel even L naught. So you're going to get when you divide L naught to this expression, you're going to get 1 plus alpha times delta T. And that's it. So now everything in this expression is known. You have to read alpha from a table, and therefore your new period T is equal to the old period T naught multiplied by square root of 1 plus alpha times delta T. So this should be the answer. So you probably have to read the coefficient of thermal expansion from a table rather than from the integrand, because they may be different numbers. Okay, let's see questions. Yes.
So why do you multiply T naught by the square root?
So here, this last expression reads T divided by T naught is equal to square root of 1 plus alpha delta T. And I just, right, this, they're asking what is the value of T. So here's, yes.
So, okay, so alpha is, we can get that value in the textbook.
Yeah, there is a table in the textbook in chapter 12, which says coefficient of linear expansion, thermal expansion of brass. The problem is that brass is alloy, right? Of copper and what else? Copper. What is brass? Copper plus and something else. What is the other thing?
Iron.
Yeah, something. So depending upon what are the proportions, you're going to have different alpha. So use the value of alpha from the table in the textbook rather than from. Okay, other, yes?
Can we do number 20 from the practice exam?
Okay, but let's see if people have questions about the homework first, and then we can go to the test.
Can we solve actually like that model? Because I tried it, but I didn't get the right answer.
So look, I make mistakes, but I think that this one is right. So use a calculator that is simple to use, and be careful, use brackets to make sure that the square root works on everything that you want it to work. And if it still doesn't work, let's talk after class. Okay. So other homework questions? Yeah.
Can we do 7?
Didn't we do this in class? We did? No?
You were genuine, and then I think you said that we wanted to wait till the next day or something.
Okay. Yeah, well, it is useful in a sense that if you're trying to lose weight by drinking cold water, you have to do a lot of drinking. This is the conclusion from this problem. So problem number 7 from the homework assignment. So here you have to deal with units. So you want the amount of energy of, in my case, 504 kilocalories. You want to convert it into SI units in joules. So you say the amount of energy, which eventually is going to be thermal energy, is going to be, for my case, 504 kilocalories. So kilocalorie is the same thing as capital C calorie. Nutritional calorie that is on the label of the food, of any food. So they don't say kilocalorie, I don't know why. They say calories only. So this is equal to 504 multiplied by 4,186 joules. So here is the conversion factor. Is this? You don't need to remember it. But this is the conversion factor between calories and joules. So once you have this in joules, you want to spend the same amount of energy to warm up this water from 0. So it is not ice, it is water at 0 to whatever is 37 degrees. And therefore, this amount of heat is heat capacity of water multiplied by the unknown mass that you're looking for of water that you have to drink, multiplied by the temperature change of this water. Between 37 and 0, the temperature change is 37. And therefore, the mass is going to be equal to the amount of heat divided by heat capacity of water times 37. And actually here you can do, you can save a little bit of clicking on your calculator by substituting Q with 504 times 4,186 divided heat capacity of water is exactly 4,186. So 4,186 times 37. So 4,186 cancels out, and you get 504 divided by 37. And you're going to get the number of kilograms of water that you have to drink. But 1 kilogram of water is 1 liter. So the answer, whatever number you obtain, is going to be also kilograms. And it is going to be a good amount of drinking. This what something like 14 liters or so. This is something like something close to 4 gallons of water. Okay. Yes. On the test. Okay. Any other problems from the homework?
I was gonna say, I don't know if this is important, but it has the density of water as 997 kilograms instead.
Yeah, it is going to affect a little bit the answer, but not much, right? And it depends what kind of water. Distilled water has one density, drinking water has another density. So I would try directly without taking into account the water density. So he's talking about the conversion between kilograms and liters. But for all practical purposes, this if it doesn't work, then you have to do the conversion with this factor of 900 and something. But I think this should work for most people. Okay, so done with homework. Okay, let's look now at any old homework problem.
So there was the one one that is talking about a steel ball being bounced over and over again, but at the same.
Multiple choice, this
was
one.
Just asking, I can't remember which chapter it was. It was like telling my.
Yeah, this is chapter.
It was question 5 on the test.
It was a homework problem too from past though, but it was just asking like why it is or is not simple.
So
harmonic.
this is not simple harmonic motion. Because look, what is the acceleration of this ball while it is in the air? 9.1. Well, the acceleration of an object that is under simple harmonic motion changes with time, and it is something like this. Changes with time. While this ball, when it is bouncing, while it is in the air, its acceleration is fixed to 9.8. So this is why it is not. Yes.
I was just wondering if like those formulas that you derived for like velocity and acceleration are going to be on the test.
Yes, those formulas are on the test, but you have to realize their meaning, right? This is why I gave this question about the bouncing ball.
Wait, so the 9.8 was the one that's being dropped and considered.
Yes, so this is 9.8.
Okay.
While harmonic oscillator that is oscillating on a spring is going to change its acceleration according to this formula. Okay, other homework? In that case, let's go to the practice test. So some of the questions on the practice test probably have wrong answers. I didn't check all of them. But so which problem was it?
21. And 40, what you said.
Okay, so 20, 21. Okay, let's start with 21 maybe because it is short. So you have a person that does this and spinning brings her arms. And when you bring your arms in, since the mass comes closer to the axis of rotation, your moment of inertia drops. And they say it drops by a lot. It drops by a factor of 3. What is the final angular speed? So this person spinning is practically not subject to much external torques, external forces, if you neglect friction. And therefore, the angular momentum has to be conserved. Angular momentum is one of the conserved quantities in nature, together with energy and linear momentum. Those are all conservation laws. If you add to them conservation of electric charge, you have a full list of conservation laws of nature. At least as far as we're concerned. Therefore, initial angular momentum has to be equal to the final angular momentum. Angular momentum is defined as a product of moment of inertia multiplied by angular velocity. So you want initial moment of inertia times initial angular velocity, which is given, it is 2.5 radians per second. To be the same as the product of final moment of inertia times final angular velocity. And from here, solving for final angular velocity, this is what they want to find in part A, you get the final angular velocity is I naught omega naught divided by I final. So the ratio of angular momenta is the moment is proportional to the ratio of angular of moments of inertia. So they say that the final is 3 times smaller than the initial. So this ratio here is 3. So this is 3 times omega naught, which is 3 times 2.5 in radians per second. So this is part A. Okay. But it is very simple. It is just keeping certain product constant. Part B, what is the ratio of final to initial angular momentum? So part B is asking the ratio of initial to final. So this question is just to ask to figure out if you know what is angular momentum. Well, initial and final are equal to each other. So what is their ratio? 1. See how? Part C, determine the final to initial kinetic energy. So when she is spinning, she has only rotational kinetic energy, and her initial rotational kinetic energy, rotational initial, is equal to 1/2 initial moment of inertia times initial angular velocity squared. They want final to initial. So the final kinetic energy final is going to be 1/2 final moment of inertia times final angular velocity squared. So they want the ratio of final to initial, so divide those two equations, and you're going to get kinetic energy final divided by kinetic energy initial. Both of them are rotational, of course, is equal to 1/2 I final omega final squared divided by 1/2 omega naught squared, like this. So 1/2 cancels out. Final to initial is 3 times larger, so this is 1/3. 1, 2, 3. And look here, omega final divided by omega final, or you can even use the numerical values, but you're going to get, look here, omega final divided by omega initial is equal to 3. So you're spinning 2 times faster, and look what happens now. You have 3 in denominator, and here you have omega final divided by omega initial squared, which is 1/3. This is 3 squared. Is 3. So her kinetic energy increases by a factor of 3. So notice that the kinetic energy is not conserved. So we have, on one hand, we have conservation of angular momentum. On the other hand, energy doesn't seem to be conserved. So this is part C. Part D, clearly, if you tripled the energy, mechanical energy is tripled, that's it. And total energy change right, in a closed system, and she's pretty much a closed system and she's spinning. Energy has to be conserved. What happened? So who was the person, the brave person that did this? Who was,
Nobody's here then.
oh. Well, you can talk with this person and see that when you do this, it is difficult. You feel that something is pulling your hands in outward direction. You want to bring them in. So you have to do work. And this work is what is increasing the kinetic energy of the person. So this means that the chemical energy stored in her muscles, ATP or whatever energy stored in her muscles, is converted into rotational kinetic energy. The total energy, if you count the chemical energy in her body, is conserved. Okay? So conservation of energy of a closed system is another fundamental law of nature. Okay. Remarks? Yes.
I wanted to ask when you said for part D, when you said that the mechanical energy does change, why is that?
So mechanical energy is for rotational kinetic energy. It changes because she does work. Practically, you can think that her muscles are making her spin faster. This is what is happening. And the total energy, which includes also the chemical energy stored in her body, is conserved. You just convert part of that chemical energy into rotational kinetic energy.
So her total energy doesn't change.
The total energy, because she is closed system, she is not subject to external forces, presumably, or they're small. The total energy has to be conserved. But the total has to include the chemical energy stored in her muscles.
That would increase by 3 also, you said?
So the kinetic energy increases by a factor of 3. So let's say we don't have the numbers to calculate how much is factor of 3, but let's say if this factor of 3 is 1,000 joules, this means that 1,000 joules from the breakfast that she had this morning was converted into rotational energy, if this factor of 3 corresponds to increase to by 1,000 joules. So this tells you actually, well, instead of drinking water to burn calories, you can spin and keep bringing your hands in. It's just as good as drinking water and get you a little bit dizzy, but so, yeah.
This might sound like a dumb question, but are there any problems on the practice exam that you're leaning on putting on the exam tomorrow?
I don't know. I'm going to write the exam tonight. I really have to you know, my time is just like yours. I don't have much time.
So you're saying you're gonna email it to us? What are you gonna put?
I wish I could, but it's not my choice. Yes?
Put this one on the exam, I think.
This one on the exam.
You should put everyone.
Well, there is not much arithmetic. You can, but I can change it in such a way that it to be different. What about that?
Well, you can change it, then you want to see the same.
Well, it is going to be the same idea. It's going to be the same idea. But let's say we can change the gender of the person from female to male and call him Bent. I say, or Andrew.
Yeah, that sounds great.
So if you don't get the problem right, you have to talk with Andrew after that. Okay,
Can we do problem number 20 now?
Yeah.
okay, let's do problem number 20. So here is problem number 20. You have, so, let's put it on the screen, all of it. Okay, so if you don't study physics, you lose your marbles. This is the idea behind this problem. Okay. So they give you the mass and the radius of those marbles, and they roll down this incline. They give you the moment of inertia of a spherical, of a solid sphere with respect to the axis that goes through the center of the sphere. And the first question is, what is the linear speed when it reaches down the, and look, the easiest way to answer here is to use conservation of energy. So here is the incline, here is a horizontal at the end of the incline, and since this angle is given to be, or it is not given, 30 degrees, okay. So since this angle is 30 degrees, and this height here is given to be 1.8 meters. You can solve this triangle. You're going to get the hypotenuse, the length of the incline is going to be, so this length from here to here is going to be what? 3.6. So call this length S from here to here. This length is 3.6 meters. You can find it with sine, cosine. Okay, and now look, you don't need that length for part A, I think, but for part A, you just use conservation of energy. When the marble is at the top, its energy is equal to mgh, gravitational potential energy. When the marble is here and rolling, it is going to have translational kinetic energy and rotational kinetic energy. So the energy at the bottom is going to be translational, is 1/2 mv squared, where v is the speed of the center of this marble, plus rotational is 1/2 of moment of inertia times angular velocity squared. It is convenient to rewrite this energy only in terms of linear speed v, because this is what you're looking for. So this is equal to 1/2 mv squared plus 1/2. So the moment of inertia is 2/5 mr squared. You have omega squared also. Omega times r is the linear speed v. So this is v squared. Cancel 1/2 with 2/5 partially. So this gives you 1/2 mv squared plus 1/5 mv squared after you substitute the product of r and omega with v. And 1/2 plus 1/5 is 7/10. And now you say energy is conserved. This marble is pretty much a closed system. So initial and final energy are equal to each other, which means that 7/10 of mv squared has to be equal to mgh. Cancel the mass, and you get that the speed v is equal to 10 times g times h divided by 7, and everything under square root. So this should be part A. Okay. Okay. Part B, average linear acceleration. So look, your speed goes from 0 to this number in a distance of 3.6 meters. So kinematically, you can find the average acceleration, right? It is, so kinematically, you know that initial speed is 0, final speed is whatever number is there, but it is known. The distance covered is s, 3.6 meters. So you have your three numbers. From those three numbers, find the acceleration. Kinematically, you need a formula that doesn't include the time. And kinematically, the formula looks like final velocity squared is equal to initial velocity squared plus 2 times acceleration times the displacement. I'm using the letter S for displacement here. Just happened that way. So for our case, V naught is 0. And solving for the acceleration, you get that the acceleration is going to be V squared divided by 2 times the displacement. So this is part B. Part B is the average acceleration. Part C, angular acceleration. Angular acceleration is equal to linear acceleration divided by the radius of the ball, of the marble. So this is it. Net torque. So part D, net torque, part D. So look, Newton's second law for rotation says that net torque is equal to moment of inertia times acceleration, right? And that's it. You have the acceleration, you have the moment of inertia, just multiply them. This is the net torque that makes this marble spin. Yeah.
Does it use angular acceleration or linear acceleration?
Angular, right? This is Newton's second law for angular motion, right? It is the analog of force equal to mass times acceleration. It is the analog of that. But you see how simple it is. Yes?
You just have to divide part B by A then, or by the radius then?
Yes, the radius of the marble is given, right? So that's it.
How did you find the displacement specifically?
I solved this triangle. So how to solve it? Let's say sine of 30 degree is equal to opposite. Opposite is 1.8 divided by hypotenuse S, right? And therefore, the hypotenuse S is equal to 1.8 meters divided by sine of 30. And use your calculator. This is what is going to, it's going to give you 2.6 meters. And part, there is one more question. What was it? Part E. Which force generates the torque? So here is the incline. Here is the ball. Which force generates the torque? Yeah.
Would be its own weight or
Well, look, it is a tricky question, but the forces that act on this ball are the gravity acting at the center, the normal force acting right here, F normal. So far, with the torque of each of those two forces is zero. The torque with respect to this axis of rotation, axis from the center. Both of those forces have zero lever arm. Their torque is zero. They cannot make the marble rotate. Just cannot. What generates the non-zero torque is the friction force. Friction force acts right here. It is static friction force, and it acts this way. Static friction force acting this way. And look, the lever arm of this force is the radius. So it is non-zero, and it makes the marble rotate.
Wouldn't it be kinetic friction just because it's moving?
Well, the point that is in contact with the surface is always at rest if you're having rolling without slipping. So it is, and actually from here you can calculate even the magnitude of this static friction force and the coefficient of friction, because the normal force can be calculated, but we're not going to go there. You can do it. And actually, if you're a mechanical engineering major, I would advise you to do it. Okay, other? Let's see questions. Yeah. Okay, do you want this problem? Okay. Okay, so there is a, so people have urgent need to have this problem and the previous problem on the test, other problems, let's see. Yes,
We do number
19,
19.
okay. Oh, this is, okay. I think I did it in one of the sections, right?
Oh, yeah. We didn't do it in
Okay, so in this problem, you have, here is the person that is rolling. Okay, I'll call this person a cylinder to avoid any misunderstanding. And I'll call the rope string. Again, not to have some misunderstanding. So they give you the mass and the radius of the cylinder. And you're releasing him from rest or releasing it from rest. And so first, free body diagram. And the free body diagram, part A, is the weight acting at the center. And the tension force, here, tension force right here, acting on his periphery, on this, or the cylinder's periphery, like this. So the part A is this. Part B, find the acceleration. So you have to look up the moment of inertia of a cylinder, I guess. But so how to find acceleration? So Newton's second law first for linear motion says that if you use what coordinate system? Let's say if you use a coordinate system with positive direction downwards, the net force is going to be the weight in positive direction, let's say, and the tension force is in negative direction. This is the net force, this expression, and I'll put it in brackets to know that it is, the whole thing is the net force. Net force is equal to what? Mass times acceleration. Unfortunately, we don't know the tension force, so we cannot calculate the acceleration. But luckily, we have a similar equation for the rotational motion. The net torque is equal to moment of inertia times angular acceleration. So the moment of inertia of a cylinder is 1/2 mr squared. Moment of inertia of a cylinder with respect to axis that goes to the axis of the cylinder. The mass of the cylinder is given, the radius is given, so you have the moment of inertia. So you say that the net torque is equal to moment of inertia times angular acceleration. Let's see what is the net torque. The torque generated by the weight is 0 because the lever arm of the weight is 0, right? Where the axis of rotation is here. The torque generated by tension force is equal to tension force in magnitude multiplied by the lever arm. Here is the line of action. The lever arm is the distance between the axis of rotation and the line of action. That distance is exactly the radius. So the lever arm is the radius. And now look, the way I have selected, I don't know if it is a reasonable choice of my coordinate system. It may or it may not be. But we defined the torques of forces that want to rotate in clockwise direction, we define them as negative. It was our convention. I don't know if this convention is going to fit with my choice of coordinate system, but we're going to see. So this is the net torque. That net torque is moment of inertia times angular acceleration. But you know that the angular acceleration is linear acceleration divided by the radius. So I can say, instead of angular acceleration, I can say 1/2 mr squared times a divided by r. Instead of angular acceleration, I'm writing linear acceleration divided by the radius. In other words, this equation reads negative torque times radius is equal to 1/2 mr acceleration. 1 power of r cancels. And here is, so now you have this equation. Negative t is equal to 1/2 ma. If you substitute that here, you're going to get mg. So instead of negative t, I'll write 1/2 ma. This should be equal to mass times acceleration that you're looking at. Acceleration kind of cancels here. Oh, this is with plus, right? This is with plus. Let me write it again because this is important. So I'm substituting the tension force with its equal. And it looks like this, mg plus 1/2 ma is equal to ma. And that's it. You cancel the mass, and you're going to, yeah. 1/2, okay. So cancel the mass, move 1/2 a to the other side of the equation. And you're going to get that acceleration due to gravity is equal to a minus 1/2 a is 1/2 a. Did I make a mistake somewhere? Well, this is what it gets to be. So from here you get that, no, this will not be the case. So my coordinate system was wrongly chosen. So if I have rotation this way, this is lifting. So my coordinate system was chosen in a bad way. I either can change the sign of the coordinate system or change the
I think you cancel out mass.
no. Look, just change the coordinate system, and this in a different coordinate system, this is negative, this is positive. So this coordinate system doesn't fit, doesn't match. So this coordinate system is the right one, because you want when this is increasing, you want to increase y. If you change the coordinate system, let's see if the coordinate system is like this, and you have negative here. This means that you're going to have, what is going to change? You have negative here, you have 1/2, okay. You cancel, you get t is half of the weight. Yes, and therefore you're going to get, you're going to get negative mg, negative, this is ma, and this is going to give me what, 3/2 of A. 3/2 of A is negative g, and therefore acceleration is equal to negative 2/3 g. And indeed, the acceleration is in negative direction as it should be. It is so. Coordinate systems. Our problem is that when we introduce angular acceleration, angular velocity, we didn't make them vectors. The textbook decided, well, there is a optional chapter saying everything is a vector, but we didn't make them vectors. And from there, you have to be very careful about the directions and the algebraic signs. But I think that this is a reasonable solution here. Okay. Part C, angular acceleration. Well, linear acceleration is this, angular acceleration is going to be this. Just divided by the radius. Part D, what is the angular speed in 1.5 seconds? So part D, angular speed in So for part D, you started from rest. Your acceleration is something that you just calculated. You need one more variable, and this is the time, 1.5 seconds. So since they're asking about the magnitude, the algebraic sign doesn't matter. The algebraic sign of alpha or A doesn't matter. And you can say that omega is omega naught plus alpha t. And that's it. Omega naught is 0, alpha calculated, t is 1.5 seconds. Yeah.
When we change the coordinate systems, the y is coming up, wouldn't that change the mass times acceleration to make acceleration negative also?
Well, this is, yeah, we make the acceleration comes out to be negative. We don't know what it is, but it comes out to be negative.
Wouldn't it cancel out? I mean, that's just.
No. This is, look, mg is in negative direction. Here is its negative sign.
Yeah.
Tension is in positive direction. And I don't know what is the acceleration. I'm calculating it and I'm getting it to be a negative number.
So what's in that equation, what's the final angular speed? What would you put in for that one?
So the initial is 0. Angular acceleration is the number that you just calculated here.
Oh, we're looking.
Yeah. And so multiply the angular acceleration with 1.5 second time. And okay. And what is the speed corresponding to this? Part E. The linear speed of the center of this cylinder is going to be equal to the radius of the cylinder multiplied by the angular velocity. Right? This is the connection between linear and angular variables for objects that are rolling without slipping. Okay, let's questions here. Well, the problem is asking about magnitudes. So what is the magnitude of acceleration? What is the magnitude of everything? So you can take absolute value of the numbers. But, well, so coordinate system has to be consistent. This is the moral of the story otherwise. So the simplification that the textbook does by saying that angular velocity is not a vector but a scalar, and angular acceleration is scalar, and angular momentum is a scalar. Everything is scalar, angular. In reality, those are vector variables. And if we know the direction of those vector variables, we're not going to have algebraic sign mistake. Okay, yes.
So just to clarify, so we, talked about, since we did problem number 2021, we talked about having those on the test. So will those be on the test then, just with different numbers?
You know what, if I answer this question, and people that are not here and people that don't look at the recording are going to be heavily disadvantaged. So I'm refusing to answer this question, but I like problems. Well, even problem 19 is a little bit trickier because of this coordinate system choice. But the other two problems are, and I cannot give also problems that take more than a few minutes to solve. Keep that also in mind.
I was actually gonna ask specifically, can we not have 19 on the test? Because it's worded really weirdly. And I just because it was taken from a British textbook, you said,
Yes.
and I didn't understand half of the phrase.
Really?
I couldn't understand half of the question.
I'm pretending to doing a similar cylinder thing is writing it in your own words maybe, because some people it's hard to understand.
Yeah.
I'm used to it 'cause I read lots of British books, but it is harder for most
But
people.
it is a normal British English. I put this problem just because of the language.
I couldn't
And the
understand.
picture, of course, the picture, just imagine a politician on the end of a rope. That's something, right? That's what's in.
If there was a diagram showing what was actually going on, we have to make the three body diagram, which is the issue, because
Okay, okay, this problem is not going to be on the test. But if somebody has strong feelings about this problem, if somebody wants to see it on the test, I'll write a version of the test just for that person. That person has to request it. And I'll give a version of the problem with this. Okay. Other questions related with the practice test or any other problems? So let me tell you, there is one problem that somebody asked about last time. That you have to be careful with this. This problem 23, you have to be careful with this problem. For that problem, you have to take into account, well, did anybody solve this problem? This problem with the mercury or whatever is in this? No?
I could figure it out. I was gonna ask if you do it next, actually.
Okay, so it is Bernoulli's equation. So the first step is to figure out the speed of the fluid at each of the points, A, B, and C. So this is the first, and this has to come from so this is problem 21, right? Or what is it?
23.
23, okay. So problem 23. So first they are asking about the speed at point A, but you better find the speed at every point. And to do it, you have to read the problem. I have to read it. Okay, so you have the different cross sections. So look, just looking at the problem, the pressure at point C, since point C is in contact with the atmosphere, the pressure at point C has to be atmospheric pressure, which is given. So what else do we need? So pressure at point C is atmospheric pressure. Pressure at point C is the answer given in pascals or in other units for the pressure at different points? I assume it is pascals. So pressure at point C is 1.01 times 10 to the fifth. Pascals. And now setting up Bernoulli's equation, points A, B, and C are at the same height. So let's say if you want to figure out the speed at point, or you have a piston there too. So the presence of the piston is going to allow you to immediately find the speed. So you have the speed at point A multiplied by the cross-sectional area at point A should be the same as the speed at point C, for example, times the cross-sectional area at point C. Right? This is a continuity equation because of the change of cross-section. So the cross-sectional areas are given, so you can immediately say that the speed at point A is equal to the speed at point C multiplied by the ratio of the area at point C divided by the area at point A. So the speed at point C is given 8 meters per second. The areas are also given. You can calculate from here VA. So it is 8 multiplied by the ratio of 6 divided by 12 is 1/2, right? So 6 divided by 12. So you have 4 meters per second is the speed at point A. Similarly, the speed at point B is area of point B times VC AC, and therefore you have the speed at point B is VC times area at point C divided by area at point B. So it is 8 multiplied by 6 divided by 5.6. And here you have to do the arithmetic because I don't see how, but it is a speed that you know it. Okay, so now you know part A, pressure at point A, how to calculate the pressure at point A. Well, Bernoulli's equation. So you say pressure at point A. I'm not going to write the height term because it's going to cancel. Plus 1/2 the density of mercury times the speed of point A should be the same thing as pressure at point C, for example, plus 1/2 rho VC squared. And here you know everything. Pressure at point C is the atmospheric pressure. The velocities you just calculated. Density of mercury is given. From here you find the pressure at point A. So you say pressure at point A is pressure at point C plus 1/2 rho VC squared minus VA. So this is part B. Part B is here, part A is here. Part C, the speed at point B. Well, we found the speed at point B, part C. The pressure at point B in a similar manner. So part D, pressure at point B. Pressure at point B is equal to pressure at point C plus 1/2 rho VC squared minus VB squared. Exactly the same way like we did the previous part B. And finally, so actually the last question is trickier because it is find the height h. So I didn't put the term for the height in any of the Bernoulli's equation expression here because they are of the same depth. All points A, B, and C are of depth equal to h. They're of this depth. But now they're asking us to find that depth. And this is tricky. It depends how you formulate the question, but you can say that the pressure right here, right at the place where this vertical part ends, is purely hydrostatic. In a sense, you can say, well, there is no any motion of the mercury there. But that pressure still has to be the same as the pressure that you calculated for part B, for point B. And and this means that so this is what you have. So here is the vertical part. They say evacuated on the top, which means that the pressure here, 0.1, pressure at 0.1 is equal to 0, it is evacuated. And here, at this unknown depth h, the pressure has to be the pressure equal to pressure point B, the pressure at point B. And the pressure at point B we just calculated. So you have the hydrostatic equation. So point B is 0.2 for you. So you have P2 is equal to P1 plus rho GH. P1 we said is 0. And therefore the height is H is equal to P2 divided by rho G. So it is equal to pressure at point B divided by rho G. So this should be, and again, it is an approximation, but this should work. The problem is that you really don't know at what spot the speed of mercury becomes 0. You're assuming that it becomes 0 here, but it's going to work. You can make a more accurate calculation, but this approximation is good enough. Okay. Okay. Questions about this problem? Okay, other problems.
We did 22.
So if that is the problem that I'm thinking. Oh, yeah, problem 22 is simple and important problem. Right? Because the result is counterintuitive. So you have aneurysm where the normal cross-sectional area is something in the place where you have aneurysm, the cross-sectional area is increases by a large factor. So here is the artery, problem 21. Here is the artery, and suddenly you have here this enlarged piece where the walls even of the artery may be weaker. You have the density of blood is given. They say here the speed in the normal cross section, so call this cross section A1, and the speed is V1, and it is given 0.5 meters per second. The first question, what is the speed of the blood here, where the cross-sectional area is A2, and the speed here is V2 is what? And continuity equation tells you that V1 A1 is equal to V2 A2, and therefore V2 is equal to V1 times A1 divided by A2. So the speed there is V1 times 1/5, 0.5 times 1/5 is 0.1. So it is not a surprise that the speed drops when you have a wider hose, right? That's not a big deal. But the surprising part is the next question. Where is the pressure higher? At point 1 or at point 2? And the answer is that the pressure is higher at the wide cross section. And if the walls of the arteries are weaker there, which they probably are, you're risking a stroke because they may break. So the pressure here is higher. So part A, I guess, part B, pressure at point 2, pressure at point 2 is higher than pressure at point 1 because of Bernoulli's equation. Right? Bernoulli's equation says that pressure plus rho gy plus 1/2 rho v squared is constant number. So when you go from point 1 to point 2, you don't change the height because it's a horizontal artery. So this term doesn't change at all. But when you go to the wider region, the speed drops. To keep the sum unchanged, you have to increase the pressure. And therefore, the pressure at point 2 is higher. And after that, they say how much higher. And you say Bernoulli's equation written in alternative form is going to be like this: P2 plus rho g, the height of point 2, plus 1/2 rho v2 squared should be the same as P1 plus rho g y1 plus 1/2 rho V1 squared. The height is the same, so those terms cancel. You move the pressure P1 to the other side of the equation with opposite sign, and I'll write the result right here. And this term to the other side with opposite sign. And you get the pressure difference P2 minus P1 is equal to, you can factor out 1/2 rho, and in the brackets, you're going to have V1 squared minus V2 squared. So this is the pressure difference. So V1 is larger than V2, and this is why the pressure difference is going to be positive. Pressure at point 2 is higher. Okay, other questions? So before we finish, let me tell you another problem that is not going to be on the test. Is problem number 14. And the reason is that in this problem, there are many approximations that can be made and they affect the answer, but they affect the answer in a small way. And the accuracy with which they give you the weights is not sufficient to determine the accuracy of the order of 1 part of a million, like some of the answers is. It's a good problem, but there are no specification if this cavity is empty or filled with air. Also, it is not clear when you're weighing this sculpture, if you're taking into account that this sculpture is submerged in air. So those effects are small, but since we're looking for a small number, they affect the answer, and the problem is not well stated. If I give a problem like this, I'm going to tell you, take into account that the cavity is filled with air, let's say, and take into account that the entire sculpture is in air with given density of air. So no problem 14, except if somebody really likes it and asks me before the test for this problem, I'll write a version of the test for that person. Okay, yes.
I was just gonna say, I think 22 would be a good one to possibly on the test, just because it doesn't take too long, the one we just did. You know, it requires work, but it doesn't take 20 minutes or longer to solve.
Well, I would agree that problem 22 is a good problem. But again, I'm not allowed to, in a large class, there is always a person that is going to be unhappy, and no matter what I do, somebody is going to complain, and so on and so forth. So let's not give more reasons for complaints, at least. But I agree, this artery problem is simple, meaningful for people that are biomedical professions. Okay. Let's in that case, let's finish it for the day. And let's hope for a good day for a test tomorrow. Yes.
So, can you help me with the Python, please?
Okay, I need a calculator, so you're welcome to come to the office and I can use my calculator, but those calculators are. So usually the difficulty in a problem like this comes from not using the calculator the right way. So, yeah.
So in that same question, you told us, you set it up for us, and you had,
Okay, let's see, which question was that?
number 5.
Okay, let's look at it now, but I count on your calculator fluency to get it right.
Because you had,
Oh, it should work. What?
it was, you had us write T naught,
Yeah,
times the square root of 1 plus alpha delta T.
Yeah.
So what would that T naught be?
She noticed 2 seconds for this version. 2 seconds.
Oh, okay.
So let's see, it should work. I don't see why. So T is T naught times 1 plus alpha delta T. Delta capital lowercase t, right? So you have to find the coefficient of linear expansion for brass. And
That's 19 times 10 to the negative 6.
so 19 times 10 to the negative 6. So you can use, let me see what are the numbers that you have.
I think 2 seconds and 154, and I did that, so I got this, and then I subtracted the 2 seconds. However, it was not right.
So they don't want the change, they want exactly this. So you have to do 2 multiplied by 1 plus this times, what was the temperature change for you?
154.
154. So this should give the answer. So 2 brackets. Oh, there is a square root, right?
Yeah.
This is under, so the brackets are under the square root.
So yeah, I did under the square root.
Yeah, I did it too and plugged it in, and mine wasn't right either.
Okay, let me grab my calculator and let's see.
Do you want this one?
No, all calculators have their own language and type. Okay, so what was the last name?
Okay. Yeah, trust me.
Okay, so let's do the arithmetic here. So you have 2 multiplied by square root of 1 plus, is it 19 times 10 to the negative 6?
Yeah, that's what
Yeah.
it said in the book.
Yeah, 19 or 18.7, I think.
Let's use more digits because what, 18.7?
Yeah, that's what I put in, but I got 2.0.
Okay, let's see what is the number that is in the
So
textbook.
in the textbook, it says, brass is linear, thermal expansion is 19 times 10 to the negative 6.
19, okay, let's use 19 then. Plus 19 times 10 to the negative 6, okay? And all of this multiplied by the temperature for you is 154. 154, and I close the brackets, and the number that I get is exactly the answer. Here it is.
Okay, yeah.
Right?
Yeah.
So let's now work with your numbers. Let's see what is the deal with your number. Just give me the name.
So we didn't have to subtract the 2 afterwards?
Why should you subtract? Look at my answer. Why should we want to subtract it?
Because I got the 2.0029, and I thought maybe.
Well, that's the answer, right? This is, why do you want to subtract it? In any case, give me your last name, I to see your version of this problem.
Sauer, B-A-U-E-R.
Conrad, right?
Yep.
Okay, so for you, everything is the same, just the temperature is 135. So let's do this arithmetic with 135. Again, the calculators are tricky tools. So here it is.
I got that answer, but I rounded mine.
Oh,
You're supposed to. Is that word decimal place? Okay, that's the issue.
well, clearly that seems to be issue. The rule is that you have to be within 1% of the correct answer. And 1% of this, you're there kind of, but not quite. 1% of this.
I plugged in rounding the next number after that, and it's correct now.
Okay. Okay, anybody else that has an issue of any type? Okay, in that case, let's end it. And I'm ending the recording and I'm going to email it. I'm going to email it. So the recording is ending. And